Right, so welcome back to che531. We're going to continue our discussion on singular value decomposition, or so-called SVD. In singular value decomposition, we can decompose any matrix, either square or rectangle, to U, W, and V transpose. U and V are orthogonal matrices, where by definition U transpose U is equal to identity, V transpose V is equal to identity, and W is a diagonal matrix. The elements on the diagonal are called singular values. So by looking at W, we should be able to say whether the matrix is, or whether the system is solvable, whether we have unique solution, indefinite number of solutions, or no solutions. Okay, so I think the best way to do that is by looking at one example. Okay, so here is the example. Assume that the sigma basically is the same as W in the notes. So this W we talked about, which is the diagonal matrix with singular values on the diagonal, in this example is going to be sigma. Now let's say I have a matrix. I did this US or singular value decomposition, or SVD, and I found that my diagonal matrix looked like this. So it has 2 and 5 on the diagonal, and then 0 as the third element of the diagonal. Okay, so I can go ahead and define sigma dagger. This symbol means dagger. Okay, so sigma dagger is, we're going to get the reciprocal of every non-zero element. So we're going to have 1 over 2, 1 over 5 for these two elements on the diagonal, and the third one we leave it at 0 because we cannot find the reciprocal at 0. So reciprocal is only found for non-zero elements. Okay, so now assume we want to solve a matrix, a system like AX equal B. Okay, and then let's say I did SVD on A, and I found this to be the diagonal elements, or the W in the notes. So W in this notes plays a role of sigma in this example. Okay, so we're going to say the solution, regardless of A, the solution is going to be always A dagger B, which means I have to find A dagger. I have to find A dagger. So here's the A dagger. Unfortunately, this actually bothers me a lot, but anyways, so we have to find A dagger and then multiply by B. So what is A dagger? A dagger is, from SVD, we know what V is, we know what U is. Okay, in other words, the SVD gives me V, sigma, and U transpose. Basically, once you do SVD, you get this form. And then A dagger is defined by V times sigma dagger, and then U transpose, like that. Okay, now the question is, what is sigma dagger? Sigma dagger is basically, you get sigma, you get the reciprocal of all non-zero elements on diagonal, and leave zeros alone. So you get sigma dagger, you put sigma dagger in here, multiply these three, you get A dagger. Then A dagger multiplied by B is going to be the solution. Now the question is, how many solutions we have? Like, is there unique, many, or none? Well, okay, so first, if A is invertible, which means all the singular values, or the sigma elements, the diagonals of sigma, if all of these are non-zero, then we're going to have a unique solution. In other words, if A dagger is equal to A inverse, there will be a unique solution. Now, if we have some zeros along the diagonals of sigma, which pretty much like this case, okay, then there are two options, either, or there are two ways. Either there is no solution, or there's an infinite number of solutions. Okay? Now, if B, the right-hand side, can be written as a combination of columns of A, so you get an A, and then if B can be written as a combination of columns of A, then there will be infinite number of solutions, if there is a 0 on the diagonal elements of sigma, like that. Okay, so there will be infinite number of solutions if B can be written as a combination of columns of A. However, if B cannot be written as a combination of columns of A, and there is 0 on the diagonal of sigma, then there's no solution, okay? And what we find from A dagger B will be the least square, or the solution that minimizes the total solution, minimizes the error. Okay, so we call it least square. So again, if B is not or cannot be written as a combination of columns of A, the solution would be least square. If B can be written as a combination of columns of A, then there should be, or there will be infinite number of solutions, given that there is at least one 0 on the diagonal elements of sigma. And if there is no 0 on the diagonal of the sigma, then there will be one unique solution. Okay, so that's how we can use SVD to figure out how many solutions we're going to get from solving a system. All right. So one thing that I forgot to say about the condition number of a matrix is that we can use the condition number of a matrix to estimate how accurate our solution is going to be. Or if you want to get, some accuracy in the solution, the question is how many or how accurate we have to be, how accurate we have to be to record the elements of a matrix. Okay, for example, if let's say if you want to get 3 decimal digit accuracy in the solution, okay, and I record up to 7 decimal digits in my calculations, then we should be able to calculate how accurate we have to record the elements of a matrix to basically get 3 significant or 3 accurate decimal digits in the solution. So there's a relation between the condition number of a matrix, the number of decimal or accuracy in the solution, and accuracy in the calculations. Okay, so if we let's say call NPC as the number of significant figures in the calculations, and NDP, by the way, this should be little d, and NDP is the number of significant figures in the solution, then we can find how many digits we have to use to record the elements of a matrix. So an example here, if you're using 7-digit accuracy, then NPC is 7, and you want to get solution with 3 decimal digit accuracy, then NDP is 3, this is 7, the difference is going to be 4. That means the condition number has to be 10 to the 4 or less. If the condition number is bigger than 10 to the 4, we cannot get 3 decimal digits accurate in the solution. So that's the basically rough estimate of number of digits in the solution, in the matrix, and the condition number. Okay. All right. So in the last section of this chapter, we're going to look at how we can basically calculate SVD in MATLAB. The function is going to be SVD. So here's MATLAB. If I have a matrix and I want to calculate, let's say here's my A, that the 2x2 matrix, 49 minus 4, 10 and minus 1. You want to calculate the UW and V, you call it SVD, and then A. And then on the left side, you say UWV. So U is going to be the first rectangular matrix, W is the diagonal matrix, and V is going to be the right rectangular matrix. Okay, and by doing so, it actually spits out all 3 matrices. So now you get V, W, and U. And when you look at the W, you see that one of the elements is very close to 0. That would tell you the matrix A is very sensitive to perturbation because we're going to have, maybe this is very close to 0 or something like 0. Okay, so having a number close to 0 on the diagonal of W, which is the singular values, tell us either the system has no solution or the system has infinite number of solutions. On top of it, it makes the matrix almost close to singular, which means, the matrix is very sensitive to perturbation as well. So SVD actually helps understand the condition number as well. All right, in the next few minutes of this video, I'd like to talk about zeros and roots of a function, which is chapter 3 in the notes. So if you have a function, you want to find the zero of the function, or so-called the roots, or the roots of the function, then we're going to look at the first method, which is called bisection method. So in this method, pictorially, if you look at the function, let's say this is the function that I'm looking at, and this function hits the x-axis at some point, and we want to find this point, which is the zero of this function, or where the function gets or becomes small or 0. Okay, so to do that, we have to start with two guess values, a and b, and our guess values should have this constraint, and the constraint is the sign of the function at point A and B should be opposite. That means if at B f is positive, at A has to be negative, or vice versa. And the reason is, if the function is negative here and the function is positive here, going from negative to positive at some point it has to hit 0. Okay, so you cannot just go from minus to plus and jump over 0. It has to hit x equals 0, well, the function equals 0 at some point. So that's why the condition is fa times fb has to be less than 0. Okay, so by checking this condition, the next step will be we find the midpoint, which is the bisection of, or we do the bisect, or we bisect the AB distance. So we find the middle point, which is a plus b divided by 2. We call it p. Okay, and then we evaluate p and compare with a and b. So if f of p times f of a is less than 0, that means the root is between a and p. Then we're going to replace b by p. However, if fp times fb is less than 0, that means the root is between p and b. Now we're going to replace a by p, or keep b. Okay? So the algorithm is written like so. First, we're going to start with some guess values, and the guess values should satisfy this constraint, which is fa times fb has to be less than 0. If not, we have to change the guess. If so, then we find the midpoint. Then we evaluate fp times fa. If fp times fa is less than 0, then we're going to replace. So if that is the case, then we're going to replace b by p. If this is not the case, we're going to replace a by p. And then we find a difference between a and b. If a and b is less than some threshold, some small number, then we stop and say, hey, the root is between, or the root is the basically average of a and b. However, if this distance or this difference is not small, if this is not small, we're going to keep cycling or iterating over this loop. Okay, so again, find a and b, divide by 2, goes to p. Then we're going to check if fp times fa is less than 0. Then we're going to replace b by p, otherwise a by p, find the difference, get the average, and iterate. So we iterate until this difference becomes small. So let me show you the pseudocode, or maybe the code, to write the bisection and find the root of a function. So here's the code. That's the code for bisection. And let's say I have a function z tan z minus 1. I want to find the root of it using bisection. Okay, so stay tuned for the next video on finding the root using bisection.